So we're going to look at the single replacement today and double replacement, which is 4 and 5. I'm going to go out of order, and I'm going to start with single replacement, mostly because that's what I wrote already. So let's go ahead and get started. So if you look at the first reaction on here, it says chlorine gas is bubbled into a solution of potassium iodide. Something I want to point out is each time as you look at these, every single one has the word solution. And if it doesn't, there's something else that I can show you in a second. So most of these, it's really important to indicate that there's a solution. Now, solution, what does that tell us? If something's a solution, that tells us it's aqueous. Okay, so that means in it breaks apart, right? So that substance breaks apart. So we should know that when we're doing this. And when you're doing these, writing these single replacement on the exam, they want you to write them as net ionic equations. So you have to break everything apart. They don't want things completely together. So that's usually what they will ask for. Okay. So let's go through one. So I'm going to put it on this paper just so I have more room. So the one that's 1986, it says chlorine gas. So I would write that as Cl2 gas because it's one of the Brinkelhoff diatomics, is bubbled into, so plus a solution of potassium iodide. So that's Ki because they both have a 1 charge. And it says solution, so I'm going to put aqueous to indicate that. And then I'm going to predict my products. So in these type reactions, single replacement means something's replacing something else. So I don't know if you remember back to honors chem, we had solubility rules. I'm sorry, activity series. So the activity series will tell you who can replace who. So here we have a non-metal is going to replace the other non-metal. So in this compound, it's going to replace the iodine. So chlorine, can it replace the iodine? Yes, it's higher than the iodine. Now, we're going to check as we go through the activity series, as we do these. I'm almost positive they don't put any that don't work on the AP exam, but we're going to go through here and see if they did, okay, as we go through these problems. And you can have, I'll post a picture of this so you guys will have the activity series. Also, you can look it up as well, but there's that. Okay, so this chlorine will replace this iodine. So over here, we're going to get KCl, okay, plus, and this is going to be I, but it's going to be diatomic because it's one of the Brinkelhoff. And we know at room temperature, this is actually a solid, not a gas. Now, KCl, is it soluble? Okay, well, let's look at this solubility rule. So we have potassium with chlorine. And if I look here on my chart, it says it's soluble. So that means this breaks apart. But and so we're going to break this apart when we get there. So this is aqueous as well. In the problem, it told you this was aqueous. So for our net ionic, I'm going to write Cl2 because this gas doesn't break apart, plus K plus I minus, right? We have to put the charges, and these are both aqueous. Again, I'm not putting it because I'm being lazy. And this breaks apart to K plus Cl minus, and those are both aqueous, plus I2 solid. Now, is there anything I can cross out? Yes, my spectator here is potassium. So that means I do need to write another reaction here. I'm going to write Cl2 gas plus I minus yields Cl minus plus I2 solid. And this is our net ionic. This was the molecular equation, and this is the ionic. Okay, and the one they want on the exam is this one. So just make sure you do that. Okay, so let's look at another one. Let's look at the one that's 1995. And you guys need to go through and do all these, but let's just do this one because it's a different one. Okay, so 1995, a bar of zinc metal is immersed in a solution of copper 2 sulfate. So again, we have a solution, bar of zinc, so that's indicating that it's zinc as a solid, plus it's immersed in a solution of copper 2 sulfate. So CuSO4, they both have a 2 charge, so they cancel out. It is aqueous. And that forms, again, so this is a single replacement. So here, this is a metal by itself. So the metal has to replace the other metal. So let's look at our solubility rules. Is zinc higher than copper? So we look at our sheet. Here's copper way down here. And where's zinc? Zinc's up here. So yes, it is. So again, it works, right? So the one by itself has to be higher than the one in the compound to replace it. So this is going to be ZnSO4 which we don't know if that's aqueous or not yet, plus copper solid. So let's look at ZnSO4. Let's see. Here's sulfate. And let's go over to zinc. And it says it's soluble. So that means it does break apart. So this is aqueous. And so let's break it apart. So we have zinc, solid, that stays together, plus this guy is soluble because it told us in the beginning it was aqueous, plus SO4, or the solution. Arrow. And by the way, you know what? I didn't check for balancing, so let's see about our balancing here. It's balanced, but you know what? I didn't check this one for balancing up here. We're going to have to go back and balance that one. I'm sorry. Okay, so this one does break apart. Okay, so that's our net. Oh, that's right, so that's our ionic. This is our molecular. Okay, so can anything cancel here? Yes, the sulfates cancel. So let's write what's left. ZnS plus Cu plus 2 yields NZn plus 2 plus CuS. And remember, the net ionic is showing you literally, what's important in the reaction that's taking place, the reason the reaction is taking place. Okay. So you can see here, like the zinc was oxidized, right, and the copper was reduced. So this is a redox reaction. Okay, let's go back and look at this one because clearly it's not balanced. So up here, so I should have done this at the beginning. I'm sorry, I just totally ran through it and didn't do it. So we need to put a 2 here to balance our iodines, and then we need to put 2 here to balance our KCl. So now let's distribute those 2s. So there should be a 2 here, a 2 here, 2 here, 2 here, and there's a 2 here, and there's a 2 here. Okay, so now that's straight. Okay, all right, sorry about that. Okay, so we've done a non-metal and we've done a metal single replacement. So now let's switch to double replacement. So this is now on your, I think it's number 4 on your sheet. So let's look at that. And you can look, I mean, it obviously is a very popular, the single replacement is very popular. It's been on the AP exam several times. You can see there. And let's take a look at the double replacement. Okay, here's the double replacement sheet. Here's what we're looking at. So we're going to have to pay attention to, remember, we're going to look at one in the future, which was the acid-base formations. And there's stuff about that here. Again, you kind of look for the word solution, and we have that again here. Solution here. We have a solution, another solution. So there's lots of solutions in this one as well. And again, that indicates that it's aqueous, so we have lots of solutions. Okay, so let's do a couple of these, and then you guys can work on them. So let's just start with the first one. So 1986, and it's sodium sulfide. So Na2S, because we get across charges, and it says solution, so it's aqueous. Plus zinc sulfate or zinc nitrate solution, so ZnNO3 aqueous. Okay, and that forms. So remember, double replacement means that it's inside with inside, outside with outside. Like they trade places. Okay, so we're going to have NaNO3 plus ZnS, and they cancel. Okay, so now we have to look at the solubility rules to see if they're going to cancel or if they're going to be soluble. So Na2, it told us Na2S is soluble. Before we do this, let's balance. Let me not forget that this time. So we have 2 NAs here. We're going to need a 2 here. That means you have 2 nitrates. So we're going to need a 2 here. And then we're also going to need a 2 here to balance the zinc. So I think that's balanced now. Okay. So Na2S, it already told us it's soluble. So that's going to be 2 Na plus, if we break it apart, plus S minus 2. Plus nitrates are always soluble. That's one that you should memorize for sure. All nitrates are soluble. And if we look, here's nitrates, and you can see all the way across, it says soluble. Right, if you look at the nitrate thing, all the way across soluble. Okay, so that's 2 Zn plus 2 plus 2 NO3 minus. And then, again, all nitrates, so 2 Na plus 2 NO3 minus plus. Okay, so now we have to look at the zinc sulfide. So we look at sulfide, and we go over to zinc, and it says here it's insoluble. So that means we just bring it down like it is, 2 ZnS, and leave it as a solid. Okay, so let's see if we can cancel anything out. Sodium's gone. It's the same on both sides. And nitrate is gone on both sides. Now, what if you had like 2 nitrates over here and 1 over here? Well, you could cancel 1 on each side and you'd be left with 1 on the side that had 2. Okay, just as a heads up. So the net is just going to be S2 minus plus 2 Zn plus 2 arrow 2 ZnS solid. So that's our net. And that's what they would be looking for. Okay, all right, let's try another one and see what they do here. Let's do 1995. Okay, so 1985 says excess concentrated sulfuric acid is added to solid calcium phosphate. All right, so concentrated sulfuric acid, so H2SO4. It means it just has like a high molarity, right? And is this a strong acid? It is, so we're going to put aqueous here. We know all acids are aqueous, but we know this is a strong acid. I'll put here, strong acid, it's going to break apart. Plus calcium phosphate, so Ca3PO4 parentheses 2, because I got to cross the charges, and it's solid, so I'm going to put an S after it. And again, it's inside with inside, outside with outside. And this is not one of those acids that breaks up weird, so should be good. All right, so let's break this up. So we should have calcium sulfate, and they both have a 2 charge, so we're going to leave like that, plus H3PO4. Okay, so now we need to balance it. So you can see here the hydrogens are we need least common multiple, right? So I'm gonna put 2 here and a 3 here. And that means I'm gonna need a 3 in front of the sulfates to balance that. And we already have that. So that should be balanced, right? We look at it. Yeah, that looks good. Okay, so now I guess it's balanced. So now we need to see if these guys are aqueous or not. This right here, this is not a strong acid. This is a weak acid. So it's not going to completely break apart. And this guy right here, let's see we'll check as we go. Okay, so sulfuric acid does completely break apart. So we're going to break it apart into its ions. Okay, so we're going to break apart the sulfuric acid because it's a strong acid. So we have 6 H pluses, because we need to multiply that, plus 3 SO4 2 minus, plus, it told us this is a solid, so we leave the calcium phosphate together. Like that, and that's a solid. Okay, and then calcium sulfate we have to look up. So let's look at our chart here. Here's a sulfate. Here's calcium. It's calcium. Okay, I think I lost my place. Calcium sulfate is slightly soluble. Okay, so this guy that's slightly soluble is tricky. And a good rule of thumb is this. If the slightly soluble substance is on the reactant side, we break it apart. Because if you think about it, some of it will react, right? If some of it's ions. But if it's on the product side and it's slightly soluble, that means a solid is definitely going to form. So we need to keep this as a solid. Okay, plus. And then phosphoric acid is a weak acid. So since it's a weak acid, this guy stays together. So we're just going to bring it down like it is. So 2H3PO4. And then it looks like we don't have any spectators here, right? So this is where the ionic and the net ionic are the same. Okay. All right, so go ahead and try the single replacement and double replacement, the rest of them, and see how you can do.